Okay, section 4.4, we are going to be talking about graphing polynomial functions. Before we do that, it would be helpful probably to define what a polynomial function is. A polynomial function is only going to occur in one variable. So we have seen polynomials with x and y's, but that's no longer the case if we're trying to graph a polynomial. We need it in one variable. And it needs to be written in the following manner. All exponents will be positive numbers, which that's part of what makes it a polynomial. There can't be any square roots of variables, okay, or fractional exponents on variables, okay? So here are some examples of polynomial function. This one's pretty standard. Most students will be comfortable with that. First one there as being a polynomial. This one got a decimal, but that's okay. It's just on the coefficient, the number out in front of x to the 18th, so that's fine. And then this last one here, we have a pi. That's okay, it's a coefficient, so that's all right. It's not in the exponent. We have a square root as well, but again, it's not in the exponent of a variable, so we're good there. And 7x to the 5th, so that's also a polynomial function. So here are some other examples of polynomial functions. One of the questions we'll ask is, what's the degree of the polynomial function? And the degree is the highest power of x in the polynomial. Okay, so this first one is a polynomial. It's a very simple one though. It's just 12, and it's a polynomial because technically we could write x to the 0 right there. Anything to the 0 is 1. So this degree, the highest power of x, is just 0, and the leading coefficient is 12. In fact, it's the only coefficient. Okay. Next polynomial here, highest power of x is 16, so the degree is 16. The leading coefficient is 9. Coefficient, again, is the number in front of the variable. And the leading coefficient means the coefficient in front of the highest power of x. Next one, x squared plus 4x to the 10th plus 18 minus 5x. This is not written in descending order like this one was. 16th power, 5th power, 1 power, 0 power. We have to go find the highest power of x, and it's right here. It's 4x to the 10th, so the degree is 10. And the leading coefficient is 4. Again, that's the number in front of x to the 10. Last one here, looking for the highest power of x. It's right here. It's 202 would be the degree. And then the leading coefficient is negative 10. With this minus out in front, that's a negative 10. Okay, so negative 10 is the leading coefficient. All right, moving on. The volume of air in lungs during a 5-second respiratory cycle can be modeled by this function where volume is the output and t is in seconds. Okay, and so we want to find, using this function, the volume of the air in the lungs 2 seconds into the cycle. So here's a great application of a cubic function, a third power polynomial. I've got this written up in Desmos here already, and the graph doesn't matter so much, but what I did want to show you is that if you type it in Desmos in f of x notation, so you can see, I think I got it right here. If you type it in f of x notation, you don't have to plug in 2 everywhere you see a t. You can just put in f of 2, and Desmos will compute it for you. So f of 2, right? So 0.658 is the answer here, okay? And so we can write this. I put f in the in Desmos because it knows how to handle f of x, but we'll write v here. So v of 2 is equal to, just plugging in 2 for t everywhere, and we got 0.658. So 0.658, and that the units there are in liters. Okay, so that's obviously it's a word problem there. Number 2, find f of a plus 2 given this function here. Okay, so remember how function notation works. Whatever we plug in for f, whatever we're trying to find, is going to go everywhere there is an x in the function, just like we did over here. I don't know if you saw it in, I didn't show it out in Desmos, but v of 2 would just be putting in 2 here, 2 here, 2 here, and then computing what that answer is. So for this one, we're going to write f of a plus 2, and I want to write it out explicitly here. So it's going to be 3 times a plus 2 squared minus 2 times a plus 2 plus 4. Okay, now if I do that, I have to be sort of careful. There's a tendency for students to want to be like, oh, well, that's just a squared plus 4. No, it's not. Let's write that out real quick. This is a plus 2 times a plus 2. This is a perfect square trinomial. It's going to end up being a squared plus 4a plus 4. Okay, so what I have here then is 3 times that, so a squared plus 4a plus 4. Oh man, I'm going to run out of space. I'm going to distribute the negative 2 here, so that'll be minus 2a minus 4 plus 4. Well, that's great. Negative 4 plus 4 is 0, so those are gone. I'm going to distribute the 3 now over everything. So I get 3a squared plus 12a plus 12 minus 2a, and then finish by combining like terms. So I'll get 3a squared plus 12a minus 2a, that's going to be plus 10a. So 3a squared plus 10a plus 12. Okay, and that's my final answer there for f of a plus 2. Just be careful when you're squaring something like that. It is not just a squared plus 4. Okay, let's move on to the next thing. Now we're really going to get into some graphical analysis here, all right? So even and odd degree polynomials. An even degree polynomial is a polynomial function that has a degree, highest power of x, that is an even number. Okay, those polynomial functions have different end behavior than odd degree polynomials. So like an even degree polynomial might be something like x to the 4th minus 4x plus 1, right? That would be even, right? An odd degree would be like something like x to the 5th plus 2x minus 17, something like that, right? Because the degree here is odd, an odd number. What this comes down to is if you have an even degree polynomial, then whether the function, whether the inputs are negative or positive, it doesn't matter. You're going to be raising it to an even power, which makes it turn to positive. Okay, and so you can see some examples here. Basically, even degree polynomials are always going to have end behavior in the same direction. So either both going down, or well, I guess these are both going down, but you could also have them both going up to both ends. Okay. Odd degree polynomials are always going to end in opposite directions. So you can see this one goes down to the left, this one goes up to the right. This one goes up to the left, this one goes down to the right. So if it's an odd degree, then it's going down or up, opposite. As you move either to the left or to the right, they're going in opposite directions. Let's do some examples where we actually apply that idea then. For each graph, find the following. We want the end behavior, so we're going to go way back to chapter 2, drag that out of your brain. And then we want to know if it's an even or odd degree. And then how many real zeros there are. Remember that zeros are values that make the function 0, which show up graphically as x-intercepts. Okay, let's start with end behavior. All right, so we'll call this EB. So the end behavior. Remember that we write end behavior like this. As x goes, we'll start with to the right. So as x goes to positive infinity, f of x goes in what direction? So in other words, as x goes to the right, which way are the y values going? Well, they're going down, right? So f of x in this example goes to negative infinity. As x goes in the opposite direction to negative infinity to the left, so, what is f of x doing, or what is y doing? Gosh darn it, f of x. Sorry, that's really sloppy. As I move to the left, the function is going down. Okay, so it's going to negative infinity. Because they're going in the same direction, we can write that it is an even degree. All right, and we can figure out the number of real zeros just by looking at the graph. How many real zeros are there? Well, there's an x-intercept here indicating a 0, and there's an x-intercept here indicating a 0. So there are 2 real zeros. Okay, you should go ahead and try the next one, see how you do, pause the video, see how you do, and then play the video and see how you, if you got it right or not. Okay. So hopefully you did that. Let's go check out the end behavior now. So as x goes to the right, as we go to positive infinity and we follow the graph to the right, it's going down, it's going to negative infinity. The y values are. So f of x approaches negative infinity. As x goes to the left, f of x is going to approach, well, let's go to the left and see what happens. It's going up. So it's going to approach positive infinity. Okay. Now we're going to go check and see if it's even or odd. Because it's ending in opposite directions, we know that it's an odd degree polynomial. Last one. How many real zeros are there? Again, real zeros show up as x-intercepts on the graph. So we've got 1, 2, 3, 4, 5. 5 real zeros. All right. And that's it for those. On the next page is a really nice, I think there's 2 charts. I'm going to go through them here in a second. But 2 charts that really I think you'll find useful. They're straight from the textbook. Sometimes the textbook does a good job of organizing some of their charts and things. So here are graphs of different degree polynomials, okay? A constant function, or a degree 0 polynomial, is just a horizontal line. Y equals 4, y equals -2. A linear function, well, you've done a ton of things with graphing lines. Those are degree 1 polynomials. Quadratic functions, those are degree 2 polynomials that we've dealt with quite a bit, especially in chapter 3. Those make parabolas. Degree 3 cubics have that odd degree behavior where they end in opposite directions. They look like this. Quartic functions, those are degree 4 polynomials. You can see they end in the same degree. You could put a negative out in front, it would end, or they end in the same direction. You could put a negative out in front, they would end going down. And a quintic function, usually we'll just say degree 5 for those, but you can see an example of those, okay? What else is on here? So yeah, so then you've got, I didn't do a lot of explaining because this was in chapter 2, but if you're confused on end behavior, you can see how it's written out here for quadratic functions, quartic functions, and then it also talks about the domain, okay? And so domain and range. So let's actually look at this real quick here. So end behavior, I'm not worried about. They write it in the opposite order, which they've changed from chapter 2 to chapter 4. I don't know why. I like my method saying as x goes here, y goes here, or as x goes here, f of x goes here. But let's talk about the domain and range. The domain is always going to be all real numbers for polynomial functions. The graphs go forever to the left and to the right, okay? The range, though, is going to depend on what type of function you have. So here, with a quadratic function, the range is going to be everything above or below the minimum, okay? And so this is saying, well, if the leading coefficient, the number out in front, is positive, then the range will be everything above the minimum. If it's an even degree and the leading coefficient is negative, in other words, it points down, then it's going to be, the range will be everything less than the maximum. So like in this example, it's y less than or equal to 0, okay? Then over here, we have odd degree functions, right? And the range on those are all real numbers, but again, don't just try to memorize that. Think about why that is the case. This function clearly goes down forever. It clearly goes up forever. Range is all of the y values covered by the graph. So this graph is going to clearly cover all the y values. Therefore, the range is all real numbers. The same thing down here. Even if we put a negative out in front of the function, this is what you've got going on. It's covering all of the y values there, so a range of all real numbers. All right? And that's the basics of graphing polynomial functions. In section 5, we'll get into more detail on like finding maximums and minimums, talking about increasing and decreasing. But for right now, that's the basics of polynomial functions. As usual, let me know if you've got any questions as you're working through the assignment. And I think that's it for section 4.